I'm sorry,
এই এই ল্যাবে যেটাতে স্ক্রিন খারাপ হয়ে গেছে ওটাতে কি পাইথন চলছিল? স্পাইডার কোনটাতে স্পাইডার না মানে জিএডিট দিয়ে করো। এটা তো বাইরের ঘরে না ভিতরেরটা বাইরেরটাতে করা হয়েছে না। যেটাতে এখন ওই সিসিটিভি করছে ওটাতে তো স্পাইডার টাইডার সবই চলছে দেখলাম।
হয়েছে।
না সেটা ভিতরের ঘরে দরজায় ঢুকেই যেটা ওটাতে তো চলছে স্পাইডার আমি এক্ষুনি বলবো। না না স্পাইডার প্যাকেজেস গুলো আছে।
All right, I think.
Okay, so welcome to the weekly colloquium at the School of Astrophysics. We are glad to have Dr. Joy Bhattacharya as our speaker today, and I will invite Dr. Subrata Chatterjee to introduce Joy.
Thank you, Rituban. Actually, it's my great honor. There are when students ask, a lot of students, I have written a lot of reference letters for students. And then there are some students, not all, where my first line or actually the last line was that it is my greatest honor to recommend this student. And definitely Joy falls in that category that it is actually my honor to introduce Joy today. So Joy was our undergraduate and master's student, and she did her undergrad. She completed her undergraduate in 2018, and this was the batch of Arijit and Anirban, who are our PhD students. And then she finished her master's in 2020, right when the pandemic struck, and all the thesis presentations and everything had to go online. Now, so Joy's batch, which also Arijit and Anirban's batch, they came here in 2015. So I have so much close emotional attachment with the batch is because in 2015 there were some issues in the department. Our former chair, Professor Shomak Raichoudhury, left, and even I was at a juncture, some of us at a juncture that okay, I'm also going to leave presidency, and that's the time when Joyce batch entered, and they were like big batch, lot of students, and many interested in astrophysics. So one of the reasons that I stayed back at presidency and had the opportunity to work with all of you over the last 10 years, and one of the reasons was that we got students like Joy, and so that 2015 batch was very close to my heart because that's the first time it seemed that we have lost a senior professor, and now everything boils down to us that how we have to motivate students and etc. So we had a lot of our former students as colloquium speakers, and I think the batch, the MSc batch that graduated in 2020, there were 4 or 5 students who actually finished their PhD this year only because it's only 5 years. And our first speaker from that batch is Joy Bhattacharya. So Joy did her PhD with Anika Peter in Ohio State University. And then she just completed, I think, in July.
Yeah, in July.
I missed her defense because I forgot about it. Sorry about that, Joy. So if we have to, give inspiration to our students about what kind of seniors they had, I would always take the example of Joy because several of you are familiar with the precision thing, right? It is now in its 10 years, actually
8 years.
8 years. And the person, if I have to credit one person, there are a lot of people involved in Arijit's batch who were the mastermind behind precision. But if I have to take one person who actually what she did is not something that will be the basis of another talk, but the way Joy led in 2017 in our bicentenary year, and how could we envision this undergraduate symposium and the precision credit goes to Joy. She was our like official quiz master, so must have worked closely with Diksha sometimes. Diksha, you had first year students when they were
Yeah.
MSc first
Yeah.
years. That's right. So now, so she did tremendous work on galaxy evolution. We'll get to hear about that. And Joy is one of the two students. The other is Shambhik Mukherjee, with whom some of you are doing your master's thesis project. So Joy is one of the two students who actually managed to write papers from both their bachelor's thesis and master's thesis. So Joy, I was very honored to co-author a paper with Joy on self-interacting dark matter, which was her master's project, working with Orko Banerjee and Shushmita Adhikari. And then part of her bachelor's work, so she did her bachelor's work with Professor Ritubal Chatterjee, and that was actually enhanced to a bachelor's thesis, which is on leisure time variability. So from leisure time variability to SIDM, to now galaxy evolution stuff and cosmology. She has worked in multiple aspects of astrophysics and cosmology. The other thing that so Joy actually got some prizes at Ohio State University, but the one that I want to mention is the Tuttle Prize, which is the Tuttle Prize at OSU for like outreach and humanitarian causes, social and outreach causes. So again, with due regards and honor to all my students who have inspired me over years, again, if I have to choose one person who probably has the best human quality, we have to, we sometimes have to nominate people for having the best human quality. I think Joy will be one of the top three students whom I immediately have in my mind that, okay, if I have to choose someone for the best human quality, Joy definitely is one of them. And I think this introduction is becoming very long, but there are reasons for it to be long because of the regards I have for Joy. So the other thing that I very proudly want to tell you is that Joy, after going to the US, this was in 2022. Yes, 2022. So I received, before that I had no knowledge of this, but in 2022 I received an email from then Shorodip Bhattacharya, now Joy Bhattacharya, that, ma'am, I have decided, because this was a personal struggle that Shorodip had for long years, and I have transformed to a trans woman. And you cannot imagine how much pride I felt, because it takes enormous courage to come up and take such kinds of step. And after she became Joy and she could establish the identity that she was having difficulty for a long time, and that actually increased my respect many more times toward Joy. And only a few days back in this department, we were talking about diversity issues, about there are gender diversities, there are class-based diversities, there are regional diversities. And so I would also invite everyone in this audience to take this opportunity so that we have somebody in front of us who was so brave and so honest, the honesty, the bravery, the self-conviction to go and express themselves to become the person they wanted. So that's a special, honor for me to introduce Joy. Thank you very much. That was a very long introduction.
Thank you so much, SC ma'am, and thank you, RC sir, for inviting me. So this is really a moment of honor, and it's a privilege that I'm here, standing here, presenting my dissertation work that I did at Ohio State University over the course of the last 5 years. So once again, I'm like indebted to Saran ma'am for whatever I've like learned. I mean, my whole trajectory in astrophysics would have been different had you two not been there in my life. And so this journey begins in 2019, 2020, when I was like applying for grad school, and I was I was very interested in dark matter, and also there was news from the LSST observatory, which was also at that time named after the women scientist Vera Rubin, also one of my inspirations. And this was in January 2020. I got my acceptance from Ohio State University also around the same time. And then I think in March 2020, everything changed. But nonetheless, things happened, and I moved to United States in Ohio to start my grad school in the middle of the pandemic. But yeah, it was basically dark matter, galaxy evolution, a little bit of like cosmology. That kind of like motivated me and guided my studies during grad school. So I'll show you this animation which says what is galaxy evolution. So what is galaxy evolution? This theory, what it tells us, how does the interplay between dark matter and gas and also stars, how do they contribute to the formation and the evolution of galaxies? Let me see if I can play this. Yeah, so this is from the Illustris TNG simulation, which I was talking to some of you. You all are also using this cutting edge hydrodynamical simulation. And so this simulation can resolve galaxy formation down to very fine mass scales. And that's why this is like very important to us. I'll be coming back to TNG 50. Let me see, why is this not playing properly? Okay, so yeah, what you see over here is the dark matter that is getting accreted and forming the galaxy, and these are the stars, and these are the dark matter, and the bottom left corner shows the gas. So this is very interesting, and since it has got to do, there is components of dark matter and baryons, this was very interesting to me. So what I then did was find Dr. Annika Peter as my advisor, and I was very inspired by the work that she was doing, studying the satellites of the Milky Way. And the Milky Way, as we know, is the galaxy where we reside in, and that is a medium-sized galaxy. And it has this disk that you see over here in the left-hand side in this image from the Gaia telescope. There's this disk of the galaxy, and then around that galaxy, there are smaller galaxies that are called the dwarf galaxies. And these dwarf galaxies was a central theme of my dissertation work. For example, the two of the largest satellite galaxies of the Milky Way are the Large and the Small Magellanic Clouds that you see over here in the lower right corner, and then you have like smaller ones like the Sextans, Draco, Sculptor, Fornax, and so on. And today we have the population of like 60 of such like satellites and we are keep on detecting them down to like lower mass limits. What this animation on the right-hand side shows is basically the orbital trajectories of those dwarf satellite galaxies around the Milky Way. So why is this relevant? This is because the galaxy, as we know, sits in its dark matter halo, and that is very, very extended. So that's for a Milky Way, that's like 200 to 300 kiloparsec. And oftentimes we don't get to like trace those regions of the dark matter halo as well as we do the disk or like the central highly dense region. But since dark matter in dark matter science, we are trying to like there's still so much of unknown there that I think we need to like probe the low density and the low mass regions which we haven't like looked into earlier. And also the technological developments are happening that are enabling progress in that direction. So, the dwarf galaxies, these are also very relevant in their own regard, and not just as satellites of the Milky Way, because they are abundantly found in a diversity of different environments of the universe. And these can be used to like constrain the cold dark matter model at the smallest scales. So cold dark matter works very well at the largest scales. For example, clusters, Milky Way, it works, but we need to understand the true particle nature of cold dark matter, we need to go down to smaller mass scales. And studying dwarf galaxies like this is one way to do that. And over here, what we see on the left-hand side is the map of all galaxies in the local volume, where you have the Milky Way and Andromeda in the center, and there are other surrounding galaxies. So while we only know this structure of the more massive galaxies in the universe, the brighter ones, the distribution of the smaller, less bright dwarf galaxies is not well known. And studying that can also can provide important clues as to the nature of dark matter. And also, if we go down to the small scale of the halos, in this plot where you see the log of the stellar mass on the y-axis and the x-axis shows the log of halo mass, you see that there is a large scatter present here. So constraining this scatter, we believe, can also provide important clues. So some of these things are very relevant to my thesis. And then there is this other problem, like I said, is that what we are unearthing is that the gravitational influence of the Milky Way kind of extends far beyond the virial radius of the dark matter halo. So the virial radius is a measure of the extent of the dark matter halo, within which its average density is 200 times average density, the critical density of the universe. This definition is, in a way, I think, like, it doesn't truly capture the nature of these gravitational interactions that we are seeing that takes place, and this goes even beyond the virial radius. For example, this shows the Milky Way and Andromeda galaxies, which you know are neighbors. And then the typical virial radius is shown by these blue shaded region, whereas like the true extent as shown by this term called the splashback radius is shown by the black solid line and the gray. So this is the black solid line shows the true extent of this of the Milky Way's gravitational potential. Yeah. So yeah, and then the thing that's taking place is, like, we are detecting more and more the faint dwarf galaxies in the low density environments, and oftentimes these are located beyond the virial radius. And what we are finding is that there are signs of interactions with Milky Way. For example, we have Leo T, Pegasus, Eridanus. These are located far from the Milky Way, but oftentimes these show the result of such interaction, namely in the form of the removal of gas that is necessary for star formation. And this, as you can see, the dates of these publications, these all have been, most of them have been coming up in the last 5 years or so. So this is a very an important topic in the community right now. So these are in beyond the virial radius of the Milky Way. They are quenched in most of the cases, which, for example, this is not Milky Way. This is, I think, NGC 2503. This is we believe is a backsplash galaxies. So, and these are also around the limit of 10 to the 6 solar masses. So these also can be reionization. These can be also backsplash galaxies. So that is still not very well understood. 10 to the 6, 10 to the 7. This is slightly massive. I think this is 10 to the 7, but I think this one is 10 to the 6-ish. Yeah. And as we know, like in those regime, the reionization kind of type of quenching also like plays an important factor. So yeah. Okay. Now again coming back into the halo. I had like gone beyond the halo of the Milky Way. So going back to the halo, there's this important question of the missing baryons and the metals in our galaxy, where we find that the luminous matter that's in the stars and the gas is only a small fraction of the baryon fraction that we would expect from cosmological constraints that include like the Big Bang nucleosynthesis and CMB. So where is this like missing baryons? So why is this question important? Because this guided me to the study of the circumgalactic medium, or CGM as we would like to call it. So the CGM is the gas that fills up this dark matter halo of the Milky Way. And basically, even though it's not like visible to us because it's very low density, but what I want to say is without the CGM, none of the star formation that we see in the galaxies would have taken place, because the CGM basically acts as an interface between the interstellar medium in the galaxies and the intergalactic medium beyond the dark matter halo. So there's, as you can see, like there's like baryonic feedback from the disk of the Milky Way. There's a satellite quenching, and often you have also like AGN, you can have AGN feedback into the CGM as well. And over here, this is a very interesting illustration that I found in this recent paper, which like shows which is basically a diagrammatic representation of the CGM and all the things that's going on. Yes. Yeah, so over here you have the ISM in the disk of the galaxy. There's winds coming out of the galaxies. There's winds coming into the galaxy that we call accretion, and also there's satellites in the dark matter halo, satellite dwarfs in the dark matter halo, and you have like stripping of their gas into the CGM. So this is also, the CGM is also a very important domain right now, and also this was the first project that I did in grad school. So once again, this is a diagram of the environment of a massive galaxy like the Milky Way. You have the massive host galaxy like the Milky Way in the center, and the blue shaded region shows the dark matter halo, within which you have the circumgalactic medium, and you have also the dwarf satellite galaxies within the dark matter halo, and you have all these interactions taking place, and what I'm showing here are the theories which can be like studied by understanding what these interactions are and some of them, like the galaxy halo connection and quenching, feature very importantly in this work that I've done. Okay, so these are like the basic questions that were a part of my dissertation. For example, what are the trajectories of dwarfs outside the very radius of the massive galaxy, and what heats up and enriches the hottest phase of the Milky Way's circumgalactic medium.
So, Joy, just one thing before you move on.
Yeah.
When you say that, well, there is gravitational influence beyond the virial radius, something like that. I mean, gravitation is a 1/r force. So
yes.
There is obviously effect. But when you say there is effect, you mean that there is some observed interaction with things that are outside the virial.
Yeah. And
you haven't really defined yet the splashback galaxy.
Not yet, yeah. But I'm foreshadowing the backsplash galaxies, which will be there in the later part of the talk. Yeah. So with these important questions, what we are the challenge that we are facing is this sheet light effect, where we are only searching under the illuminated part that is just below the lamp post, but we are not able to look around in the more darker regions. So and it might be that the answers lie outside this illuminated region. So that is why there is we need to consider low mass galaxies, dwarf galaxies here, and also in like the low density environments, which are not because most of the studies have been in like either the ISM of the Milky Way or these dwarf satellites like LMC and SMC, which are very close to the Milky Way. But as once again, as I said, there's LSST coming up, and this is like the first slide that we had from like June this year. We are very excited about this, and in fact, I'm also working on developing a pipeline related to this observatory. We are very excited about the science prospects of this telescope, and we believe that this will be able to answer many of the questions that I showed in the slide earlier. So this is how my dissertation is structured. The first is this work on the circumgalactic medium. Then I show this work on the low surface brightness galaxies. And finally, this is on the bright LMC and SMC analogs. And these are basically arranged as the distance from the Milky Way. So the circumgalactic medium, as we know, in the virial region, less than 200 kiloparsec. And then you have beyond the virial radius, the infalling and backsplash region, and finally the field region, which is very isolated with respect to the Milky Way. And then, yeah, so am I missing a slide here? Yeah. Yeah, so coming back to the CGM of the Milky Way, which I told you was a very low density nebulous gas that fills up the dark matter halo of the Milky Way. And we characterize the very hot component of this, which is at temperatures greater than 1,000,000 Kelvin. And we know that if a gas is this hot, it will emit an X-ray. And this emission will be dominated by the oxygen, some of the oxygen and the neon lines, the oxygen 7 and the oxygen 8, which are highly ionized states of oxygen that you see in this like temperature versus density plots. So if we can find the emission lines from the oxygen and also neon in the X-ray emission along some sight line, then we might also be able to like characterize the circumgalactic medium. So there was this prior work by Soumashkriti. She was also a student of Presidency University, and now she's like a Hubble Fellow at Stanford University, and she has done great work on the circumgalactic medium of the Milky Way using X-rays and also the SZ effect. I see, yeah. So she was basically my mentor for this project, and she had this earlier work which showed the characteristic both in like the left work is an absorption spectroscopy, and this one is an emission spectroscopy. But this was along the Blazar 1ES1553, which is located along close to the central axis of the Milky Way. But we needed to like look at a sight line which was away from the central axis of the Milky Way, because along the central axis you have some things called the Fermi bubble and stuff, which I can talk about later if you want. But we needed to look at away from the Milky Way, and MRK 421, which many of you know, the Blazar, which I also studied with RC sir. So this is a very bright Blazar, and there's plenty of archival data available. So using that data, I sought to study the emission spectroscopy in this project, where I used XMM Newton, particularly the EPIC MOS2 spectra. So this is the very bright Blazar MRK 421, and after carefully removing any of the emission from the Blazar itself, I extracted the spectra basically from this annular region where this contamination was very less. And so from that spectra, I first tried fitting with a single temperature plasma model and then a 2-temperature plasma model. Yeah, so what I found was that for the 2-temperature plasma model, I had a better fit, and this showed that there's like multiple component and not just like a single component. So we have the warm-hot virial component, which is shown in the here in the spectral energy distributions, where you have the energy times the flux on the y-axis, and the x-axis shows the energy. So the error bars that you see, the black points, these are the measurements from XMM Newton, and you have then the best fit components, the blue being the warm hot, the virial component, which is closer to million Kelvin, and then you have the red component, which is the hot or super virial, which is like more of a 10 million Kelvin. So this is what we found here, and it wasn't for these two, for this single sight line. We also found this for 5 other sight lines, all within 5 degrees of MRK 421. And this is what we found here. So over here in this plot, the y-axis shows the emission measure, which is basically proportional to the density of the circumgalactic medium, integrated along density squared, integrated along the line of the sight, and the x-axis shows the temperature. And once again, we found 2 cluster of points, the top left being the warm hot, the warm hot component, and then you have the hotter component. So there were a couple of interesting things here, which I'll probably not be covering in the interest of time, but we can totally discuss later. So there were something like these bias and scatter, which we looked at, that was down to the chemical makeup of the circumgalactic medium. So, and also we found that this scatter was due to the fact that the CGM is inhomogeneous at those small scales. It's not. So there's like spatial variations in that, and that's also has become an important topic of research. But in all, to summarize, the main takeaway from this work was that we detected the circumgalactic medium in an anti-galactic sight line, which, like I said, was away from the galaxy, which shows that it isn't like, say, AGN activity or some sort of feedback in the center of the galaxy that can be attributed to the CGM, but rather something which is happening in the whole disk of the galaxy. And this was a key takeaway of this work. Then moving on to yeah, once again, I think that's the most well-studied blazar, so we had lots of archival data for that. Yes, and also the anti-galactic satellite, that was also an added benefit of that. So far I've talked about the circumgalactic medium, and you found out that there's hot gas at 1 million Kelvin present over there. But and what this hot gas can do is, or like any gas can in the CGM, what it can do is it can remove gas from the satellite dwarf galaxies through this process called ram pressure stripping. You have these results from these 2 works where these are like simulations, and you can see that so they are like losing their gas content as it like flows through some sort of like other hotter material. So this can lead to this process called quenching. So what is quenching? Quenching is when star formation stops in a galaxy, and so because the galaxy has lost its gas and it has no more gas left to form stars. So that is quenching. And this is usually seen in these, like in the dwarf galaxies that are located close to a massive galaxies, because like I said, ram pressure stripping, tidal interaction, it strips their star forming gas. And this is very well shown by this plot here, where you can find that most of the dwarf satellite galaxies which are within the virial radius of Milky Way and Andromeda, that they are very gas poor, because the y-axis shows the H1 gas content, and the x-axis shows the distance to MW or Andromeda. Whereas what we find over here is that most of the dwarfs that are present beyond the virial radius are gas rich, that they have enough gas in them and they are able to form stars. However, there's an exception that the LMC and SMC that you see over here, even though they are located very close to Milky Way, they are still forming stars. And that is because of the fact that the LMC is very big. It's like 1/10 the mass of the Milky Way. So since it has its own very deep potential, well, it is still able to hold on to gas. But if for the other dwarf galaxies, which are smaller, there's no chance, and they have stopped forming stars.
How many how many do you know dwarf galaxies of Milky Way were detected?
So for Milky Way, I think like SMC and SM, as we can see, there's no other like blue square over here. Within the virial radius, there's like only.
How many dwarf galaxies is expected that Milky Way is having?
Okay, so the expectation is basically we are trying to like constrain CDM based on the numbers that we are detecting. The ones there was a missing satellite problems, now we have like, so that is gone because we have too many satellites and we are keep on like discovering as the detection capabilities are getting better. So and yeah, and like I said, we are still now discovering new stuff out over here.
About 50 or so is known, right?
60, I think, the latest number. Yeah. And these days, like there's a paper every day, every week in arXiv where we are detecting some very ultra faint dwarf galaxies, if not around the Milky Way or Andromeda, around like some other nearby massive galaxy.
The CDM prediction is like few hundred or thousand.
Yeah, so I think that is down to like completeness and everything. So far we are doing good in terms of that. I mean, there is no tension in that front compared to how it was 10 years ago. But yeah, we are discovering many of these interesting systems. So oh, for the lowest, so last year there was this system called the UM1 Ursa Major 1. I think that was the name, that had a stellar mass of 16 solar masses.
But that's a dwarf galaxy.
Here's the thing, it is so small that like we are confused as to whether it's a dwarf galaxy or it's a star cluster, globular star cluster. So and that is, so we are trying to right now do simulations to like study things at those 16 solar masses, or order of 10 solar masses. Yeah, so there were a couple of few RGB stars, and most of them were like the subsolar sort of like stars. So yeah, this was last year, and there is heavy interest with that. Some people are saying it's like only the CDM cusp of it is left. The rest of it has been stripped. Based on that, they were doing a timing analysis, but that's the only one. And I think people are searching for such stuff all the time. Yeah. Yeah, so here I'll present two questions that like motivated my rest of my dissertation work. And the first is, what is the extent of a massive galaxy's influence on star formation? And this is best shown by this plot on the left. So both these plots show the quench fraction. So in each bin, we are finding the fraction of galaxies which are already quenched. So we call that the quench fraction. On the left-hand side, you have on the x-axis the distance to the nearest massive galaxy like the Milky Way or larger. And on the right-hand side, you have the log of the stellar mass. I'm sorry, this is coming in. Yeah, the right has the log of the stellar mass. So these are the points are all in bins of the distance and the stellar mass over here. So for the first question, there is this very important work by Marla Giha from 2012, where we plot the quench fraction in terms of distance. And what we find is that the quench fraction doesn't fall to zero right at the virial radius. So the virial radius would be to 300 kiloparsec, and that's basically this tiny sliver over here. But it's still non-zero up to 1 to 2 megaparsec. Once again, which again shows that the extent of a massive galaxy goes beyond its virial radius.
call a quench fraction? How do you define the quenching? Like
Quench fraction is basically in this work they use the SDSS data, so they have this DN 4000 sort of measure. So I think that maps onto the quenched whether the galaxy is quenched or not. So based on that, they are classifying each galaxy as red or blue. I think that is the the best method. Otherwise, for example, later in the work, I use color to, but oftentimes like color or morphology often doesn't like match very well with the quench fraction. But like for that, spectra is needed, and you only have it. It's difficult to obtain for large surface. So yeah, so the quench fraction is non-zero even at 1 and 2 megaparsec. Yeah. So the colors corresponds to the stellar mass of the galaxy. So as you can see, these are mostly like bright satellites like the LMC and SMC. So these are like from 9.75 to 8. Yeah, like LMC and SMC. And on the right, the question was, how do bright dwarfs in the field, bright dwarfs as in like LMC and SMC, respond to their environment? Or, I mean, they are found to be mainly, these are predominantly star forming. As you can see over here, at around 10 to the 8 and 10 to the 9 solar masses, the quench fraction is very low. And this is across like these multiple surveys in different environments. And what is in those systems that like facilitates this active star formation? So this was the second question that I looked at. So for the first question, which was what is the extent of a massive galaxy's influence, I worked with this catalog of around 24,000 low surface brightness galaxies in the dark energy survey. And for that, this was my team of collaborators. So there was this paper, this work by Tanoglidis et al. That presented this catalog, and we had this. We have these very interesting systems, even though they are low surface brightness. But I was interested because, like, we keep on seeing these objects everywhere in the universe, especially with like dark energy survey, HSC, and now especially with LSST, and these come in different like forms. For example, many of them are blue and red. So what is the significance of blue and red? So blue means that you have the galaxies are dominated by the O and B, very massive stars, and these are also very young. So these are actively forming young galaxies, actively star forming young galaxies, and the red ones are mainly the old red stars. These galaxies have most of these stars because they are quenched and they have like stopped forming stars. So what I looked at was what are the environments, the locations where these LSBGs are located at, and for that I did a statistical analysis. But before that, I'll show you my target sample. So the right-hand side shows the map of the dark energy survey footprint, where each point here corresponds to a low surface brightness from the catalog, and these are colored by their G minus I color. So G and I are the magnitude bands that we have there, and so basically G minus I color is also like corresponds to the color that we see. So what we find is that the red LSBGs are clustered in certain regions of this footprint, whereas the blue LSBGs are more uniformly spread out. Yeah, this is the DES footprint. So this was from the year 3 sample, and I think the year 6 sample is coming out also early next year. Yeah, and then what we looked at was, where do we have the massive galaxies present? Because we showed that the massive galaxies exert some influence on these dwarf galaxies that causes them to like transform from either red, from blue to red, that is from star forming to quenched. So for the massive galaxies, we looked at the ZOM sample, which provides the stellar mass and like distances of these Milky Way and LMC analogs in the local universe. Local universe as in like it goes up to like 70 megaparsec, and this was their stellar mass. So these were the galaxies and analogous to Milky Way and the LMC. And then what we did was we used a friend of friend algorithm to like classify their environment. Some were in the clusters, namely they were concentrated in the fornax, which is located here, and then there were also isolated, the isolated massive galaxies which do not have any nearby massive galaxy. So as you can see, like the places where the red LSBGs were clustered at is also where the massive galaxies are clustered here as well. So what we did was we performed this process called stacking of the radial density profiles, and then we did the background subtraction. So the y-axis shows the projected number density, and the x-axis shows the projected separation from these massive host galaxies. And this was basically for 2 bins of the stellar mass of the host, and we find that there is even after background subtraction, we find that there is a slope like this, showing that the LSBGs are concentrated within the virial radius of the hosts. And even outside the virial radius, like it doesn't like drop down to 0. There's still a trend there. And then what we did was we separated out the LSBGs in terms of their color, as in we called those which have G minus I less than 0.6 as blue LSBGs, and those which were greater than 0.6 as red LSBGs. And what we find is that the red LSBGs were more numerous around these massive host galaxies, because as you can see, there is a difference in normalization, and this is also background subtracted. So this this difference in normalization shows that red LSBGs tend to cluster more around the massive galaxies. So then what we did was we looked at that color surface brightness distributions in terms of these Hess diagrams for the LSBGs, and what we did was we separated we put them into 2 bins. The one which was within the virial radius, which is shown on the left-hand side, these which we call the satellite LSBGs, and on the right-hand side, these are beyond the virial radius, which are called the backsplash and infalling LSBGs. So if you look at this closely, you find that there is a feature over here at around, say, a G minus I of 0.7. And since this is towards redder color, this is basically this is showing a quenched population of LSBGs. And what we are seeing that this sort of feature is even present at for outside the virial radius. So once again, we are establishing that the LSBGs are probably quenched even outside the virial radius of the massive galaxies. And then what we did was we marginalized these distributions, just looking at the G minus I color, and we found that there is an excess present at 0.7, 0.8 with respect to some distant field LSBGs, which are very isolated from any massive galaxy. Yeah. Is a distant field LSBG. So they do not have any massive galaxy within, I think, within 1 degree, not within 1 degree, they do not fall within, I think, 4 or 5 times the virial radius of any massive galaxies there. Everything is in my same sample, yeah. So they are, yes, we do see this separation, and we also use the case statistic to show that this is very significant. Yes. So this is the, as you can see, like this is present for both the LMC mass host and also the Milky Way mass host, even beyond the virial radius. So in a nutshell, this paper, I think, was one of the key takeaways was like we were able to use these LSBGs, which people haven't dealt with much before, to study these gravitation interactions. And this we did using photometry, because since these LSBGs are low surface brightness, extracting their spectra is very difficult. So, and since we do not have the spectra, we do not have their distances. So we had to do things in like projected separation, do the background separation. But yeah, that was the crowning achievement, that even with whatever was available, we were able to like robustly show that this excess was present. Yeah. Now, I talked about infalling and backsplash region. Now, let me tell you what backsplash galaxies are. So this is very this is a very exciting sort of systems that I was drawn to, and also this was some work that Sushmita Di also did earlier. So these are galaxies which have a very peculiar orbital history. So what they do is, suppose you have like something like a Milky Way sitting here, and the solid white line is the, say, suppose the virial radius of the Milky Way. Sometimes galaxies, so usually what happens is, for example, the LMC and SMC, they get accreted onto the Milky Way. They fall into like this, and they spiral closer and closer to the Milky Way, and they fall into the potential well of the galaxy. But in some cases, if the galaxy happens to have a very eccentric orbit, what happens is it will come into the dark matter halo like this, complete a pericentric passage, and then it again goes out like this. So these are very rare systems, but it has been shown that many of these exist. So this is an example in simulation. This is, I think, is this Illustris? Probably this is Illustris. So these are some of the examples that you see over here of backsplash galaxies. And what happens is, since they complete this closed pericentric passage, during that time they are quenched. That strips their gas, and they are not able to form stars. But again, once again, they again end up outside in the field, where usually most of the galaxies are star forming. So you have these like dwarf galaxies which resemble the satellite, the Cohen satellite galaxies, but they are sitting in the middle of the field. These are the backsplash galaxies, and like they were kind of you saw them earlier in the low surface brightness work. You'll see them again in the next project that I did using TNJ50, which I said is a very superior simulation, which lets us simulate dwarf galaxies down to very low stellar masses over a large cosmological volume. And this was the last project of my thesis, where I looked at the field dwarf galaxies. So usually people look at the satellite dwarf galaxies, which are around Milky Way or clusters, but there's not much of emphasis on the field dwarfs, which reside in these dark matter halos, which mass is less than 10 to the 11.5. And also I took a stellar cut of less than 10 to the 9.5. So they were comparable to, once again, the LMC and SMC, which we call the bright dwarfs. So yeah, so this was the relevant sample in this work, and what I studied was their star formation and their environments, particularly the density of the environments where they're situated in. So this plot over here on the left is a map of the TNJ50 simulation, the X and the Y coordinates here. And all of these galaxies have been color coded by their star formation, specific star formation rate, such that the blue things that you see are actively star forming, and the red things are quenched. Once again, they have lost their gas, and they are not forming stars. What we find is that the red quenched galaxies happen to be found in the very dense regions of the simulations, whereas the blue things are found in like the voids or more of like the filaments here. So this is one important clue. And then over here on the right, you see the overdensity parameter, which is a measure of the environmental density of the dwarf galaxies with respect to the halo mass. So what we find is that our relevant sample over here, they are mostly located in the very low density region over here. But still, even though most of it is blue here, there's still this curious kind of fraction of them that are also very red. So where is this red quenched dwarfs coming from in the field? So to study that further, I looked at, once again, I did the quench fraction plots of in bins of stellar mass on the left-hand side and the distance to the massive galaxy on the right-hand side. And once again, look that our sample of interest is this bluish green line over here, and this is less than 11.5. And once again, what we are finding is that in all cases, the quench fraction, yeah. Quenched, I did in terms of distance from the star forming main sequence. Yeah. Yeah, so the black is the complete sample. These are in the more dense halos, which are in the Milky Way and the cluster size, and the blue are the bluish green. Yeah, yeah. So once again, they have very low quench fraction. That is mainly on account that these low mass halos also sit in the low density environments of the universe. And then I studied what I call the star formation histories. I wouldn't be going into this very in detail due to I think, I'm sorry, I'm running a bit late on time. But yeah, so I divided my sample into primaries, secondaries, and last but not the least, the backsplash galaxies. And once again, what we find that is that the cumulative star formation histories in terms of the look back time, that the backsplash galaxies have a very different distribution compared to the primaries and the secondaries, and that they have like mostly formed most of their stars earlier, say like 5 giga years ago, as compared to the primaries and secondaries that are still forming their star to this present day. These are on TNJ50. Yeah, so I looked at the dark matter halos. So the most massive galaxy became the primaries, and then there were secondaries. And then the backsplash were mostly the primaries, which had completed that orbital. Yes, yeah. Yes, the snapshots. Yes, and also for this, like for this star formation history, you have to like go back to each star particles and find where they were when they were formed to like make this plot. Yes, yeah. Yeah. Yeah.
Galaxies.
Yeah.
Are you following the galaxy throughout all the simulations and tracking each galaxy?
Yeah.
If they were in a backspace?
Yes. Yeah.
Okay.
Yeah, like that.
And tau 50 and tau 90?
Yeah, they correspond to the epochs at which the galaxies from like 50% and 90% of the stars, because this is used in both like observations and simulation based studies. Yeah, and then what I show is that most of these quenched dwarfs that I showed earlier are located in the denser environments at less than 1.5 megaparsec, where these are dominated by this quenched backsplash population, and which I showed have different distributions. So last but not the least, another important result of this work was I showed the two halo galactic conformity effect, where I showed that the more massive host galaxies, the dwarfs which are located close to the quenched massive galaxy also happens to have a larger quench fraction. So this was observed for more massive galaxies in the universe in observations, but we showed this for dwarfs in this simulation. So this was a very nice, interesting result in this work. And also, as far as galaxy halo connection is concerned, there was something. There was this thing where we found that the stellar mass on the left-hand side and the gas mass of these dwarf galaxies, they point to one particular thing where, due to tidal stripping, they have lost their dynamical mass, which is like the total mass of the galaxies. But the fact is that the backsplash are red, are quenched, whereas the secondaries, which have lost due to some tidal interaction, they are still star forming, and that is. Yeah, so the left panel shows the stellar mass, and that is the gas mass. And the squares are the backsplash galaxies, the diamonds are the secondaries. So the key result is that the secondaries are still forming stars, even though they are deficient in dark matter, because they are only interacting with a dwarf scale primary, whereas the backsplash are interacting with a cluster or a Milky Way mass primary. Yeah, so this is so yeah, these are the results that for the questions that we had earlier presented in this presentation. And then I will also highlight these three other supplementary work that I've done. So I was also associated with this this Marian collaboration, and it was a privilege to interact with all my collaborators there, where we are studying the dark matter halos of star-forming dwarfs in the universe. We are collecting their photometry based on which we are doing like weak lensing measurements in order to study the galaxy halo connection at a greater level of precision. And then this is a very recent work. This is actually something that I started in the April this year, and I've been doing this on and off, where I'm studying their morphologies using the legacy survey imaging, using non-parametric indicators like the Gini index, M20, concentration, asymmetry, smoothness. So this is what I'm working on now. And also recently, I'm working on developing a pipeline to search and characterize dwarf galaxies in Rubin LSST photometry. So this is the data preview one that we had in June this year, and then we soon have like a data preview 2 next year. So these are some of like the visit images. So I'm like developing a co-addition pipeline for these in order to study the low. So what we find over here is basically a low surface brightness galaxy. So that we are doing over here. And so these are the questions that I will explore further in my future career. And with that, I would like to conclude my talk. Thank you, everyone.
Questions? Yes.
Yeah.
So I have a few, but yeah. So I think I'm missing something because it's probably very easy that I'm not getting this. So again, I'm coming to the flashback radius. So first of all, is the flashback radius something which is almost analytically derivable, or is there a closed equation?
There it is, and it can be analytically derived, and we have also seen measurements in, for example, the I know there's a paper by Shushmita Deep where
So
we
yeah, so what I'm trying to say is that probably in a smaller simulation, you fit some equation and you have an analytical expression for your
yes.
flashback. That sense, I was asking that you really need to track all the galaxies and or just maybe go around these flashback radius and find galaxies that you need and call them flashback galaxies.
No, I think we need to track. Especially with simulations, we need to track, and whereas identifying them in observations is a bit more difficult, because then you have to like look at their star formation histories and stuff, which we can like get an idea by studying star formation histories. But like in order to like say eliminate any other process, for example, reionization based quenching, that is more that is a little bit non-trivial. So that's why we can always talk about backsplash candidates, but never. Yeah.
Yeah. But, oh, right. So what is exactly that you are tracking? So I understand you are tracking the entire time. So do you track like a galaxy is coming very close?
Yes.
Mass and going back, okay?
Yeah. First, I'm like selecting all those galaxies which are beyond the virial radius at the present day, and then I'm like going back and tracing their. Yeah. Because in my work, like there was this other second class of galaxies which were infalling, but they still lost their gas. And I think I showed one plot over here. There was this other group which also like released their paper at the same time as mine. They showed that the stripping due to cosmic web that was taking place.
Like I would assume that there would be some galaxies which do not have a very eccentric orbit, but they are just grazing, losing some mass, and yet they would land up away from the virial radius.
Yes. Yeah, there are those cases as well. So I think right now we need both observations, simulations to probe systems in a better detail.
Other questions? Yes, Siddhartha?
So can you explain the effect of ram pressure stripping in the quenching fraction?
Yeah, so RAM pressure stripping is what happens for these dwarf galaxies at say 10 to the 7, 10